Hello, everyone. It's September 30th. Another late night. My God. Another day just buried in papers and trying to understand. Um, I did have to go back to textbooks to learn, kind of from ground up, what kernel methods are. And it's actually quite helpful to have I wouldn't say full understanding, but a better understanding of what kernel methods are, or what the kernel tricks are, what it stands for, right? So you have a better understanding of this, and then all the properties of kernels, and how those mappings work. And I understand what kernel PCA is, right? Well, these are all good, but coming back to the paper, there's still a lot of things I don't know, and it's something I just figured out, but it's still I'm not 100% sure. And there's some trick involving the centering matrix, which I think I got it right, but I'm not 100% sure. There's still a problem where the constraint, right? They put the variance and covariance constraint to a identity matrix. I don't understand 100% why, but I think I'm gonna let it go. And there's some more analysis I just have to skip. It's just too thick, right? Too thick for our good. I need to get down to analyzing the data. But on that front, I might be able to do a better job at separating my data. So currently, it's just pure PCA, right? It's not even PCA. It's just SVD. Currently, it's just SVD. We isolating the direction that the data in its current form mostly vary, which it's a linear transformation, right? It might be that we need a kernel to do a kernel PCA to raise it up, right? Raise it up to higher dimension, and we'll see. I mean, what type of kernel should we use? I don't know, but we can definitely try. I mean, the two most popular ones, we can try both and see if they make the separation a little bit easier. And this method that's in this paper, my God, it's been like 2 days, right? Knee deep in this mud. Still, no end. Like one page can take me a whole day to finish. I don't know. I don't even know if I want to implement it because the implementation has a lot more nuance into it because I need to find the algorithm, right? Because it's a semi-definite programming problem, so I need to find a way to solve this. I think there definitely are libraries out there that can solve convex optimization problem. I'm not worried about that. I mean, the thing is, I can just go to the algorithm, I go to the pseudocode, and then just do that without understanding anything. But I want to understand. I want to understand what type of method they're using, and it's helping, right? I just every day, it's kind of dragging, right? Dragging every day. All right, anyway, so today's goal. So yesterday, we used a very convoluted way to solve this problem. And I have the good method. Where is the good method? This is the good method, right? I still not 100% understand, so I'm trying to understand it one more time today. And if we have more time, we go back to the other one. But as of right now, let's just decode. This is today's challenge. A message containing letters from A to Z can be decoded into numbers using the following mapping. To decode an encoded message, all the digits must be grouped, then mapped back to the letters using the reverse of the mapping above. That's fine. So this one can be 11, 10, and 6. 11, 10, 6. Oh, how many different ways we can decode it? I see. Or 1, 1, 10, 6. But we cannot have leading zeros, right? Given containing digits, there are a number of ways to decode it. Okay, so backtracking, right? DFS plus backtracking. So we always take 1 and we do the remainder. Then we take 2, then we do the remainder. And that's it. And we will do, because we always do the remainder, so I just need 1 index. Right? I need 1 index and go for the remainder. Let's try. Let's see if you can code it up fast. Yeah, man, I really want to move forward. Oh, we have to move forward today. Yeah. All right. Let's see. Seems to be just a def DFS, right, index, and then return an int. So I just want to know from index to the end how many different ways can we do. So we always take 1. Oh, if it's a 0, that would be interesting. Oh, I need to also build the map. It's actually a reverse map, right? Mapping. Let's say stri for I in range 1 to 27, right? And this will correspond to, I just need to know the way, so I don't really need, I don't even need to have the mapping. Like, it's not necessary, right? It's not necessary to have the mapping. No, it's not necessary. So the difficult thing is it has to be 26, right? So 1 to 26. And if it's a 0, it's a 0, then it's nothing, right? You cannot decode if it starts with 0. Because if you start with 0, you cannot do 0, and you cannot do 0 something. So that's that. So it's like we can say if s index is equal to 0, right? Then we return 0. That's nothing. And if index is equal to len s, return 0. Right? Both are not good. Otherwise, we do 1, and then so otherwise we'll say we'll take the first one, and then we do the remainder. Right? Or we take the first 2 and do the remainder. So I'll take the first one and do the remainder. So res. So okay, possibility 1 shall equal to DFS index plus 1, right? Because we take the first one, definitely works. Possibility 2 shall equal to DFS index plus 2. Take 2 if int s index 2 index plus 2 is between 1 and 26. I mean, it's definitely going to be larger than 1, so you don't have to worry about that, because I removed the 0, so it just have to be this, right? Else it's going to be 0. You just cannot take 2. And then we return possibly 1 plus possibly 2. And of course, we can say from functools port cache. Alright, I'm going to cache this thing. Don't forget cache. Okay. So I'm going to return DFS 0. Let's see. We have 1, 2, which give us 2 we have 226, give us 3. We have 0, 6, give us 0. And finally, we have this 11106, which give us 2, right? Yeah, I think this gives us 2. S. What the heck? String out of range. Of course, string out of range. This should go first. My bad. What else? Huh? How? How is string index out of range? This is bonkers. I already have return already. Oh, larger equal to. Alright, this is worrisome. The heck? Oh, because it's always 0. Damn. Hold on. So I want, this is how many ways? This is how many ways? So it's at the end, right? At the end. Yeah. We should say, if this equals to 0, then we should say if lightness is equal, not lightness. If s is equal to lightness, I didn't do this. S index, right? And it's not 0, so that will return 1. I forgot to return. And if index is equal to lightness minus 2, right? And this thing smaller than 26, I'll return 1. No, no, this is fine. And I'll have 2, right? I can, hold on. No. I feel if this is, shouldn't return 1, which means I have gone through the whole thing. Nope, that's not right. Hold on, let me think again. We're taking this, so that's one way, right? And if this one returns 0, shouldn't it be... Man. Yeah, hold on. This is definitely right. If it's the last one, right? If we go to the last one, if it's larger, then it doesn't do anything. So yeah, so the number of ways is determined by this. So if these two is good, then I go 2 more. And if this should return 1, if I have 2 left, then I shall do 1, and I know it's not 0. So I'll do this and plus this. Okay. So I'll do, if it's I'll do DFS index plus 1, then plus this is smaller than. Otherwise we do this. So I shall do this plus maybe I can do this. Hold on. I can return this plus DFS index plus 2 times this. Alright, so this we definitely can do, and this, depending on whether this, but this, what if this is 0 and this is good? Oh, then we'll hit this case. Right, we'll hit this case. True. I'm gonna int this. Okay. Now this looks promising. I'm gonna throw some. So 100, right? Okay. $100 test case. Print str. No. Type join. Join what? For this in range 100. Rand int 0 to 9. Oh, have to be str this. Maybe too much. You know what? That's too much. Let's do 10. There we go. This is a better one. Oh shoot, we have to print the. Okay, we have to print the parentheses. Not parentheses, the quotation marks. All right, let's test this. Okay, I think it's right. Oh wow, I've done this many times. Okay, that's it. Yeah, not too shabby. Let's see. It's pretty standard. It's pretty standard backtracking. Now you won. What's the runtime? Well, I think it's ON. because everything is called once. Yeah, because I do this, I think it's on. Pretty standard backtracking. DFS with this DFS with DP. We compute the total number of decodings from index, from some index, right, from some index towards the end, and cache it. And for any given index, we add together the two possibilities. DP index plus 1 plus DP index plus 2. Now the condition here is that S index cannot be 0, right? Cannot be 0. And S index to index plus 2 must be between 1 and 26. I got a little bit bogged down by the anchor case. Anchor, how do you spell anchor? Oh man, is that anchor? Is this anchor? No. Holy crap. Ship anchor. Anchor. Anchor, Jesus. Yeah, I have 4 in this case, covering all possible ending conditions. Alright, so what we do now is we're gonna compare. That's probably a good solution. Okay. Ooh, look at that. That's also DP, but it's slightly different. So up into this position, how many we have? Current. From I minus 1 to I. So just I is here. Right? We want to check the previous 2. And we want to find out how many that they hold. P is the number of decoding from front to I, okay? From front to I, that's the number of P, and a PP is the number of decoding from front to I minus 1, okay? So I have from the front to I and front to I minus 1, so I have 2 values. So now I am at a new one, right? I'm at a new one. So the number of decoding is going to be I minus 1 plus I minus 1 plus I. Actually, I'm gonna try this. This is actually a pretty smart thing, and it's always good to practice different DP thoughts. Because my way of thought DP is, you control this and then you can consider the rest. You throw the rest of recursion. But this is a different way of doing DP. So this is a different way of doing DP, where we consider that that the number of decodings from decodings in Si and Si minus 1 have been solved. Now we are at Si plus 1. How do we proceed? Well, we proceed by checking whether Si to I plus 2, right, is within range. If it is, we add S to I minus 1. Call it P. Call it PP. Proceed by checking is in range. If it is, we add PP. Then we check whether Si plus 1 is, but in this case, I might just say minus 1. This will be minus 2. It'll be easier, right? Then okay, so we check this. And then we can check this. And if this is 0. If it is, then if it is not, right? If it is not, we add P. Yeah. So we can say I don't have P minus 2. So I can say PP and P is 0. And P, it should be, okay, what's the length? Do we have a 0 length? No, we do not. So we just say it's going to be int S0 is equal to 0, not equal to 0. If it's not equal to 0, then we have. Otherwise, we don't have. And then we say for I in range 1 to minus. Okay. All right. So in this case, we're gonna first check because I want to use. So we say current equals. I want to check Si minus 1 to now it's I minus 1, right? Check I minus 1 to I plus 1. If this is, because it's 2, so it's going to be 1, 0, smaller or equal to this, smaller or equal to 26, right? So we say if this, then we can int this times PP. Oh, hold on, because PP starts with 0. And this is the first one. So shall times PP times 1 if I is equal to 1, else PP, right? And then current plus equal to, now we do 1. So it's Si is not equal to 0, and I'm going to int this times p, right? Because it's not 0, yeah, times p. So once we're done, we're gonna say pp and p equals p and current, because current is here, right? And then this pp is gonna be p, right? Then when we're done, we should return p, right? Yeah, I actually like this one. Jesus.